This question actually came from my Discord and Patreon community, so thanks, Chad, for this question. And that was, what are the actual bottlenecks that we're seeing between here and Singularity? So, without further ado, let's jump in. Just as a quick recap, Moore's Law has been in effect for about 120 years. The transistor age was preceded by the vacuum tube age, which was preceded by mechanical relays, or electromechanical relays, which was preceded by purely mechanical computation. So when you take a look at the grand arc of history, for 12 decades, we've had reliable, predictable improvements in terms of the cost of calculations or the efficiency of computers. And so they have gone up many, many orders of magnitude in that amount of time with no signs of slowing down. Now, this is the primary thing that people like Ray Kurzweil and I rely on when we say, hey, if this trend continues, we're headed for like a reliably predictable future. So let's take a look at what, if any, constraints might exist between here and there. Now, one thing that you have to keep in mind, this is kind of the framing logic for the whole thing, is what's called the law of constraints or the theory of constraints. The theory of constraints basically says that in a system, there is always going to be one primary bottleneck or constraint, one source of friction that slows the whole system down. And a consequence of that is that any improvements, any optimizations made in the system not at the bottleneck don't really have that much of a net effect, meaning there's always going to be one primary thing that slows you down. And then what happens? So the second consequence is, even if you eliminate one bottleneck, then there's going to be another bottleneck. So as a former infrastructure IT guy, this was my life. So we would look at bottlenecks like the amount of RAM that servers had, the amount of CPUs that they had, the size of the database, or the network throughput. So there's basic food groups in every complex system in terms of, okay, in order to get specific work done, what are the constraints? How much data can you move? How much processing can you do? And you get really interesting network effects. I promise the story will be quick. So as an example, if you had a database server that didn't have enough memory or didn't have a large enough cache size for queries, then it would take exponentially longer to run a query, because rather than just saying, hey, let me read the database into memory, it would have to swap it to storage, which is 1,000 times slower. That's kind of a rule of thumb. I don't know if it's literally 1,000 times slower. It depends on the system. Anyways, so then you have a query that instead of taking a second, takes 1,000 seconds, and that slows everything else down. It's like a traffic jam. So law of constraints, think traffic jam. One lane gets removed further down because there's a car accident or because there's work going on. Instead of going 70 miles an hour, you're now going 5 miles an hour. That is an example of the theory of constraints in real life. So moving on. First and foremost, silicon seems to be the primary bottleneck. And so what I mean by that is silicon chips. And it's not a bottleneck because it's not a permanent bottleneck. It is a bottleneck insofar as it takes time to improve. Now, what I'll point out, though, is that the concept of neural networks, from perceptrons and everything else, like the stuff that Jeffrey Hinton and Jan LeCun did, the thing that they're famous for, they did back in the 80s. We've had neural networks for 40 to 50 years, depending on which one you're looking at. But it wasn't until computers were good enough to run them at scale that now suddenly we're close to AGI. So one way that you can interpret this is that maybe silicon technology, maybe the chips, the fundamental hardware limitation, is the primary bottleneck. And with that, you might say, okay, I've seen the video. Once we solve that, it's inevitable that we will get to AGI and superintelligence and all those other things. That's kind of what reality seems to be demonstrating, and that's what Ray Kurzweil predicted. So, maybe pack it up, we can go home. However, there are still going to be some other potential constraints where AI specifically is concerned, so we will unpack those. But just keep in mind, neural networks are nothing new. Artificial neural networks are nothing new. And it almost seems as though it was inevitable that as soon as computers were powerful enough to run larger neural networks, guess what? Someone ran a larger neural network and they discovered new ways of doing things. So it's just like, once you have a new tool, a new capability, you explore new ways to experiment with it. So next up is data. Now, last year, we were all worried about the data wall. Even, Andre Karpathy and others have been saying, hey, there's only one internet. We've used literally all human data. The rest of it is mostly noisy and low quality. Like there's only so many Mr. Beast videos you can train on. That's not necessarily going to help you generalize to, invent nuclear fusion. Even if you watch every Mr. Beast video a million times, that won't get you any closer to, solving aging or those sorts of things. So not all data is created equal. Now, what has happened, though, is that there has been a slew of papers demonstrating different ways of using self-play. So this is basically a pure reinforcement learning mechanism where instead of training on more and more data, you have these models that are already bootstrapped. They already have intelligence. They already have self correction and error detection at a certain level. But what you can do is, in the same way that AlphaGo learned to play Go at a superhuman level, it didn't play against humans and it didn't have the data. It just played against itself. What we're finding now is that you can actually do the same thing with math, with language, with everything else. And so you basically are taking this wild internet data, which is mostly low quality, and you're distilling it repeatedly through things like distillation and self-play and all these other reinforcement learning algorithms. And so data is actually not a bottleneck. We thought it would be, but that data wall was breached relatively quickly. Now, that doesn't mean that we won't find other limitations, because one of the things that people are worried about is like, well, AI isn't really able to generalize beyond its training distribution. I think that we're going to start to see papers coming out probably pretty soon, certainly by the end of this year, demonstrating how these AI models are actually starting to generalize beyond their training distribution. In fact, when you with certain long context problems, even with Sonnet 3.5 and 3.6, if you know what you're looking for, you will see when it generalizes beyond its training distribution and it's making inferences, it's triangulating truths or things that must be true or might be true outside of what it actually knows. I've personally discovered this because I've been dealing with chronic illness. And when I've been having really long conversations, I'm like, okay, what are these, like, which of these things that you're saying are facts that you knew from your training data that you have a high confidence in? And what are these other things that you're remixing and you're saying must be true or might be true based on first principles reasoning? These models are already capable of first principles reasoning, which is a big deal. So moving on, I just wanted to say data is not likely to be a permanent bottleneck, even if it consumes all human data, because there is a functionally infinite amount of symbolic data that you can generate. I asked ChatGPT 01 to figure out how many possible novels you can write, and by the way, all the reasoning models can do this, and it comes down to something like 10 to the 50,000th. So for context, there's only 10 to the 80 atoms in the universe. So once you have symbolic reasoning, or semantic reasoning or mathematical reasoning, then you functionally have infinite data that you can generate. There's an infinite possible combinations of text and math that represents everything else. Now, granted, the vast majority of that is not going to be useful, but you just separate the wheat from the chaff, and that's literally what they did. For the chain of thought reasoning, they just said, just generate a bunch of them and pick the best ones. So you can find the signal in the noise, you can find the pattern in the chaos just through brute forcing, but they'll probably find better ways. All right, I've rambled enough about data is not a bottleneck. Moving on. Next one is energy. So, people are worried about like, oh, AI uses too much energy, it's bad for the environment. There's not really much evidence to support that. Like, okay, you can reason from first principles that like, well, they use GPUs and GPUs use a lot of energy. But at the same time, like crypto still uses way more energy than AI. But furthermore, the energy use of silicon wafers or silicon chips is an inverse proportion to the density. So basically, proportional. What I'm saying is, as transistor density goes up, as chips get more efficient, the energy that they use per computation is going down exponentially. So while computational ability is going up exponentially, energy cost is going down exponentially. So in the long run, energy is not any more of a bottleneck than the silicon is itself. And then furthermore, there's actually a virtuous cycle here, and that is that AI, particularly as it's getting better at material science, is starting to help us with fusion. It's helping with solar. It'll help with bio and other renewables. So it's kind of a self-solving problem in that AI is, like as Marcus Aurelius said, let the obstacle be the way. And so AI will actually help create energy hyperabundance. If for no other reason than the fact that it will demand more electricity means that the market will say, hey, we need to produce more electricity and fossil fuels aren't necessarily the best way. Maybe let's build some more solar. Let's build some more nuclear. Let's build some fusion. And so it could actually kick off a lot more inspiration and innovation. Same way that NASA did with the space race. It's like, well, the technology we need doesn't exist, so let's invent the technology so that we can get to the moon. In this case, the technology that we're trying to, or the moonshot is, let's build super intelligence, and there's a few technologies that don't exist to get us there, so let's invent those technologies. So energy is certainly not a permanent bottleneck, and it might actually be the inverse, where like in the effort of solving artificial intelligence, we solve energy, which then solves a whole bunch of other downstream problems. And I mean water shortages, because if you have energy hyperabundance, you can desalinate however much water you want, which solves agriculture, which solves all kinds of other problems. And that's just looking at water. If you have energy hyperabundance, you can decarbonize the atmosphere. Like the number of problems that energy hyperabundance would solve is crazy. All right, moving on. Real quick plug for my Substack and Twitter and Patreon and everything else. It's all available on my Linktree, and I'll have more stuff coming to my Linktree soon. I'm working on a few books, and yeah, you get the idea. So, anyways, back to the show. Just now you're aware. Click on the Linktree. Link is in the description. Next up is algorithms. So basically, the debate here comes from: do you need deep neural networks or do you need something else? And some people still say you need neurosymbolic, but I'm like, AI is neurosymbolic because it works with tokens, which are symbols. And I know that technically, well, actually, that's not what they're talking about. But the point is that deep neural networks, large language models, work symbolically. And they are neural networks, and they've also generalized to literally every domain. The rule of thumb is that if you can represent it in data, a neural network can figure it out. So the idea that deep neural networks were necessary but not sufficient to get to general intelligence and then super intelligence, that assertion seems like it's evaporating. And so when you look at okay, they can do text, they can do math, they can do video, they can do audio, they can control robots. In fact, the latest robotic models that are coming out, they're training end-to-end monolithic droid brains to run the whole robot. That's not something that I would have thought. I would have thought that it would probably be easier and better to have disparate models, to say, here's one model for locomotion, here's one for speech, here's one for vision. But they're saying, no, they're integrating them all into a one-size-fits-all model. And it's not just one company doing this. It's a bunch of them. As I think it's, is it Figure? It's Figure or one of the startups, but also NVIDIA is doing the same thing. So you get this, it seems like the paradigm of just scale the networks, just make the network bigger and deeper with more parameters and more algorithmic tricks. It seems like generative AI is, or diffusion. So there's the, I guess they're both generative, but there's the next token prediction, and then there's diffusion models. Those are the two primary deep neural networks that we're working with right now. It seems like those generalize well enough, and that paradigm is not just necessary, but is also sufficient to keep us going further. And even if it doesn't get us all the way to super intelligence, I know that I'm preaching to the choir because I've run some polls, and the vast majority of you in my audience believe that this current paradigm will at least get us most of the way to the AGI, if not beyond AGI. And then it can help with those next paradigms to get to super intelligence, whatever the difference happens to be. Anyways, moving on, algorithms don't seem to be a bottleneck. One of these that does seem to be a real bottleneck is money. And the reason is quite simple, is you look at the graphs, each next frontier model costs exponentially more. That trend is not reversing. It's that simple. It has to do with the amount of manpower that goes into it, the amount of energy, the amount of compute. It's the aggregate of all the resources, all the capital and labor that goes into training the next generation of models. If that trend were reversing, I would say money probably isn't a bottleneck. But if this trend continues for another 2 or 3 frontier models, it could get to the point where like we have to pool resources in order to train the next frontier model. That might actually be a forcing function. Can you imagine what if we get to the point where Microsoft and Google and Alibaba and all of Europe, what if we get to the point where we actually need to come together as a species to invent superintelligence? What if it actually becomes so expensive to train these things in terms of energy and silicon and labor that you actually can't do it in the market? What if you actually have to get over ourselves as a species and say, yes, we are all going to commit to training superintelligence? Kind of like in the Bruce Willis movie Armageddon, when it's like the whole planet comes together to, send Bruce Willis off to blow up the asteroid, like so that we can all, survive. It might be a kind of inverse of that, where it's like, okay, if we want to get to superintelligence, everyone has to pool their resources. If the trend continues, that's a future that we might be looking at. In which case, AI might actually solve global conflict because it's like, you know what, we're all deciding to commit our resources. They also did that in the movie Contact. So anyways, just a thought. I don't know if that's the direction it's going to go. We might find some efficiencies, but we might still have diminishing returns. But right now, the data shows pretty clearly that money might be the biggest bottleneck, other than silicon itself. But then, of course, money can solve the silicon problem in time. So time is also a constraint. Anyways, I'm rambling. Next up is humans. So basically a scarcity of geniuses. There's only so many Ilya Sutskevers in the world, right? And so, or Noam Browns, right? There's only so many people at that genius level who know so much about this stuff that their insights really move the needle. Now, what I will say is that there is a few mitigations to this. So while there's only so many Ilya Sutskevers, there is the open source contribution. So even though there's a lot of closed source research going on, a lot of these companies still publish some of their research, not all of it. And even though you can't have, even though there's closed source AI, those companies also have revolving doors because non-competes are not legal in California, which is where a lot of this research is going on. So someone goes to DeepMind, they learn a whole bunch of stuff. Then they go to OpenAI, they learn a whole bunch of stuff. Then they go somewhere else and learn a whole bunch of stuff. So you have this cross-pollination that's happening even without open source. I think open source would be better for the world, but China's publishing stuff, America's publishing stuff, Europe's publishing some stuff, but it's mostly America and China. Now, one thing that I realize, though, is that this limitation of human geniuses is actually a relatively short-term constraint. Once we get to probably later this year, if not early next year, the AI models will be better researchers than most researchers, which that means that suddenly you have this snowball effect of, instead of having a few thousand AI researchers or 10,000 AI researchers who are really good, then you functionally have 1 million or 1 billion high quality AI researchers globally. And that only gets better over time, by the way. When you see the benchmarks where it's like, oh yeah, Sam Altman was saying that OpenAI has like, a top 50 coder in the world. And by the end of the year, they expect to have the best coder in the world. You apply that to math, you have the best mathematician in the world, the best coder in the world. What is AI? It's math and code. So if you have an AI model that is the best AI and math coder, or the best at AI and math in the whole world, then suddenly human geniuses are not the bottleneck anymore. So this is a temporary constraint, and it might be alleviated by this time next year. So it is a bottleneck right now, but it's not gonna stand up for long, I don't think. And finally, the really biggest bottleneck is our own stupidity. We are so far from the physical limits of what is computationally possible, and we are so far from the theoretical mathematical limits of what is possible. So it's fear, it's stupidity, and it's violence are the biggest bottlenecks, honestly. Whether it's regulatory capture or regulatory friction or gung-ho politicians who are just trying to signal how woke they are to their voter base or whatever, fear-mongering doomsday prophecies, or just straight up human conflict, just being warlike. Those are honestly the biggest barriers between here and Singularity. If you look at if you go all the way back to the main graph, there's no evidence that we're slowing down. it's going to keep going, right? Computational efficiency is going to keep going up and to the right. The only people that can stop us are us. We are our own worst enemies. So thanks for watching. Cheers.